Hey guys, let's start our third part of the Deterministic Finite Automata or DFAs. Let's see what we got for this session. In the previous lectures, we learned DFAs in action. Now we know many things about the DFAs. We analyzed the behavior of DFAs. We trace machines. We design some DFAs. And also, we introduced as a tutorial a new tool called JFLAP. So we are so ready for what? Designing with JFLAP and also continuing the template that we follow so far. Okay, so let's start with another design, and we are gonna use JFLAP for this. Okay, so here is the set builder: a to the n, b to the m, n greater than or equal to 0, m greater than or equal to 0 over this alphabet. And the question is requesting to design a DFA to accept this guy. Okay, so to have a feeling about what strings are this, so it is saying that any number of A's followed by any number of B's. Okay, so for any number of A's, we already know what does it mean. Let me bring up my JFLAP. And so this is my JFLAP and finite automata. So it opens a canvas here. All right. Any number of A's, we already know we need to make this guy as an initial state. Since lambda will be accepted here, as you see, n and m both can be 0, and this will produce lambda here. So we need to make this guy as final state as well. Okay, what else we know here? Any number of A's, we need to keep the flow of the strings here. So we just click on that. So we create a loop here. So any number of A's goes here. We keep the flow of a string to stay on Q0 by this loop, right? Okay, so what would happen when we see the first B? Then we need to create another state here, and we need to move the flow to the Q1. You see here, any number of B's should be accepted. In this way, we put a loop here, and any number of B's will be accepted here. So I need to make this guy as an final state as well. Okay, so at this moment, with this design, all of the string, any number of A's followed by any number of B's will be accepted, right? Now we need to create a trap to reject the rest of that. How can we do that? We already know how to do that. So we create a trap here, and then A, shift enter, B. So this is my trap. Okay. Now we start analyzing our design so far. You remember I said we need to have one outgoing for every symbol of the alphabet. So when we are on Q0, for A we have in this loop, for B we have this to the Q1. So we don't need anything else for the Q0. We are done with the Q0. How about Q1? We have one outgoing for B, but if after the B we have A in the string, we need to guide it or move it to Q2, which is our trap. So if after the B we have A, we need to send it to the trap. Okay, this is the design that will fulfill A to the N, B to the M. All right, we may test it with some test strings. So A, any number of A's, it should be accepted. If M is equal to 0, then any number of A's should be accepted. So up to here, it should be accepted. B should be accepted. BA should be rejected, right? So B goes to Q1 and A goes to the trap. So BA should be rejected, BBB should be accepted, and ABABB should be rejected. So let me run it and see what would happen. Okay, so the only strings that should be rejected is BA, because B goes here and A goes to the trap. A, B, A, B, A. So after the B's, any A will goes to the trap. So it should be either any number of A's followed by any number of B's. After that, any A will go to the trap. And this is how it is rejecting this guy. All right. And lambda should be accepted as well. Let me check lambda here. So enter lambda and run it again. And you see lambda is accepted too. We are not done with this example. The example is asking something else. Let me see, what is that? Design a DFA to reject L. Here we design a DFA to accept L. Now it is asking design a DFA to reject L. So when we say to reject L, it means it should accept L bar. So its equivalent is design a DFA to accept L bar. How can I change this to accept L bar? Okay, after some struggling and some brainstorming, probably you will reach to this algorithm. If I change the role of each state differently, I mean, if it is accepting state, I change it to regular state. This one as well. And if it is regular state, if I change it to accepting state, then the same machine will accept L bar. So that's a very useful algorithm. Let me do that. So I change this. I remove the final state, I remove the final state, and I change this to final state. So with these simple changes, we construct a machine that accepts L bar. We can test it. For this, the same input that we already had, you remember that this BA was rejected and this one was rejected too. Now, these are the only things that are accepted. The rest of that should be rejected. Let me run that code. You see, BA is accepted now. ABABB is accepted. And even the lambda is rejected too, right? So, the role was reversed. Exactly, it was reversed. Okay, based on this knowledge, let me summarize the algorithm here. How to construct a DFA to accept L bar. First, construct a DFA to accept L, and then turn all accepting state to regular state, turn all regular state to accepting state. That's it. All right. Sometimes this is a very useful thing. Sometimes when you look at the L, it is a very hard to design a DFA for L. So in that case, if you can figure out that L bar is somehow it's easier, so first create a DFA for L bar and then use this algorithm to change its role. Here is some exercises that put here. All strings with no more than 3 A's, all strings with at least 3 A's, and we have another set of the exercises. Exactly 1A, exactly 2 B's. At least 1A, exactly 2 B's. Exactly 2 A's, more than 2 B's. So you see, these are very important exercises that give you a very good idea and skill about designing DFA. Let's look at our template and let's see where are we and what materials left for covering. Okay, we had 8 steps and so far we finished up to here. So the automata in action. All right, so we will have formal definitions and also we need to discuss about the power and what would be the next step. So let's start with formal definition. Okay, formal definitions. How can we mathematically define DFAs? A DFA can be defined with a quintuple or 5-tuple. And here is how this 5-tuple look like. We have Q's, we have the sigma or alphabet, we have delta function, Q0 and F. Let's see what are they one by one. So the Q is a set, is a finite and non-empty set of states. So you remember we said number of states should be finite and it should be non-empty because if the set of the states is empty, we don't have any DFA, right? So it is a set, it is finite, and it is non-empty. So the Q is defined. What is the sigma? The sigma is a finite and non-empty again of symbols, and this is called alphabet, and we are so familiar with that. What is delta? Delta is the transition function. We will discuss about that in detail in the next slide. So it is called transition function or delta function. And it is defined like this. So this is the delta, the name of the function, and this is the domain, which is a Cartesian product between Q and alphabet, and the range is Q. And the point is the delta should be a total function. That's a big story there, and we need to go over it in detail, why it should be total function. What is the next one? Is next one the Q0, which is the initial state, and F is the set of final states. So if we have all of these 5 elements, we can construct the machine. And if we have a machine, we can extract these 5 elements from the definition or the design of the machine. So we need some exercise about that. But before that, let me review one more time that what are these 5 tuples? The Q is the set of the states. The sigma is input alphabet. And the delta is delta function or transition function. Q0 is initial state. And F is the set of all final states. All right, let's take some examples. What is this machine? We are so familiar with that. So it is any number of A's followed by a B will be accepted. And this is our trap. This is an instance of a machine. Now the problem is find all elements of M. So it's very easy. What is Q? The set of the states. So regardless of the type of the state, it is initial, it is final, it is regular, we just enumerate the states. So Q0, Q1, and Q2. So we are done with the Q. What is the alphabet? So we look at the symbols being used here. It's just A and B. So this will be our sigma. For the delta, I will discuss in the next slide. What is the Q0 or initial state? Yeah, it happens to be Q0. So the initial state is Q0. And what is the set of the final state? And it's easy too. So the only final state is Q1. So I owe you the delta function or transition function that I will discuss in the next slide. For working with the transition function, we need to elaborate a little bit about its definition. So the delta is defined by this, right? What is this? It is the Cartesian product between Q and the alphabet. So what is the Q? Q0, Q1, Q2, cross, what is the alphabet? A, comma, B. And we know that how to create this Cartesian product. So the Cartesian product is a set of ordered pair that one from here and one from here. So Q0 A, comma, Q0 B, comma, then Q1. Q1 A, and so forth. Yeah, the last one will be Q2 B. So this is the domain of this machine. What is the range? The range is just Q. Yeah, let me make it a little bit neat. So this is the domain and this is the range. Now the question is, what is the function rule? The function rule, we can read it from this design. For example, Q0A, it means that if you are on Q0 and if you read the input A, what the machine does, it stays on Q0. So whatever the machine is going to do is its range. In other words, so delta of Q0 and A, it means that if machine is on Q0 and it reads A, then where it moves, it is equal to, based on this, it loops Q0. Okay? How about delta of Q0 and if the input is B, we see that it goes to Q1. And if we continue and write all of them by algebraic notation, then we will get this. And for example, this guy, Q2B. So if we are on Q2 and when we read B, it is saying that stay on Q2. So the result will be Q2. This is how we specify the transition function. And if we want to draw the Venn diagram, then we already are familiar with that. So Q0A goes to Q0. Q0B goes to Q1. So all of these stuff, we already had some practice on them. Here we need to note that the delta or transition function is a total function. What does it mean? if you look at the all of the domain members here, you see all of them are defined. And each subrule is one transition. As an example, this is the algebraic notation of the delta function. And just for example, look at this one. Delta Q1A is equal to Q2. And you can find it here, Q1A, and it goes to Q2. And it was equivalent to one transition like this. All right. So it means that every member of the domain is representing one transition. Now, with this knowledge, let me ask this important question. Why delta is total function? What would happen if delta was not total function? Okay, so it means that it was partial function. And what is the meaning of the partial function? It means that at least one member was undefined. So then what? Maybe you are asking, okay, so if it was partial function, what could goes wrong? To understand this, let me modify the delta function by making one of them, as an example, the first one, Q0A, this one, as undefined. And let's see what would happen. By reverse engineering, let's see what would be the effect. If we remove this guy, and this will affect this guy. So there is no loop here, and there is no outgoing transition if the input is A. Do you see what we are going with this information? If the machine is in Q0 and if the input is A, then machine doesn't know where to go. That's the problem. If it is partial function, it means that at least one of them, one or maybe more, are undefined. And when we say undefined, it means that for this input, there is no transition. And if it happens for this DFAs, machine doesn't know where to go. And that's the problem. To resolve this issue, either we need to define a new behavior for that. For example, hey, if the machine doesn't know where to go, machine stops. So we need to redefine all of this stuff again. But the second option is we prevent delta being partial function. And the second option was picked by the mathematician. All right. But we have some other machines, other classes of machines that will be introduced later. In that case, this strict rule was relaxed a little bit. Now let's look at the delta from other angle. Actually, this is what I explained before. If we have a state like this, and if we have this alphabet, if we want to have total function, then it means that for every state, we need one outgoing for every symbol of the alphabet. And this is actually called DFA's constraint. So DFA constraint is very strict, and it means that at any time frame, there is always one and only one transition. That's very strict. As I said, for the other classes of the machines, this strict rule will be a little bit relaxed. We have some exercises here. I gave you the machine and I ask you to extract this information. We have another exercise here. I gave you the 5 tuple information and I asked you to construct the machine. This is another one. Now let's talk about transition table. So far, for representing transition function, we mentioned 2 ways. One way was algebraic notation, another way was Venn diagram. I want to say in this slide that we have third way or third method to represent transition function, and that's using the transition table. Let me explain that with a simple example. So just look at this algebraic notation of a machine. That's the same machine that we have seen so far. All right. So how can we create a transition table for that? We create this table like this. So this is the name of the function. These are the alphabet, and these are the set of the queues or states, right? And how we represent every subrule of this delta function. Yeah, we need to find the Q0 from here and A from here, and then this guy will be the range value. Okay, and let's take another example. For example, here, the Q2, we find the Q2 here and the B here, and then this will be the range of this. So we can fill out this table, and this is another way to represent transition functions. What is associated language to DFA? We know that every DFA is designed to accept a language, right? And just remember that what is a language? Of course, we are talking about formal language, right? What is a formal language? It's just a set of strings, right? So every DFA accept a set of strings, and that set of string is called associated language to that DFA. So here is how we define the associated language to a DFA. Let's call that as an M, for example, is the set of all strings that M accepts. And we denote that with L of M. So the language of this machine. All right. And we can actually extend this definition to every other machines that we will learn later. Another question is equivalency of machines. When can we say two machines, M1 and M2, are equivalent? When both of them have the same associated language. So when L of M1 is equal to L of M2, then these two machines are equivalent. Okay? Just remember that this definition can be extended again to all types of machines. For example, let's say we have one language here and we create machine 1 here and we create machine 2 here. If both of these two guys accept the same language, right, then these two guys will be equivalent. This machine can be DFA. This machine can be even something else, another class of machines that we have not covered yet. But since both of them accept the same language, then we call them equivalent. Another important question is what is computation that every computer scientist should know. When we say we are computing, really what we are doing. So let's start from here that when you start your machine, the machine start with a configuration that we call it a starting configuration. And then when the machine starts running, the machine goes from one configuration to another configuration, then from that configuration to another configuration. This moving from configuration to another configuration continues until the machine halts by accepting or rejecting the string. So eventually machine halts, and this sequence of configuration is called computation. You see how beautiful it is? So computation is actually the sequence of configurations from when the machine starts until it halts. So it means that computation is actually accepting or rejecting a string. It's nothing else. Accepting or rejecting a string or processing a string, right? And that's a very, very important concept. What is determinism? So I owe you the meaning of deterministic. When we said deterministic finite automata, what is the meaning of deterministic? All right. Now let's look it up from the dictionary and see what is the meaning of determinism. So in fact, this is an philosophical concept. And when you look it up to the dictionary, it said the belief that all events are caused by things that happened before, and that people have no real ability to make choices or control what happens. So it means that with 100% certainty, something will happen. Now, what is the relationship between this determinism and computer science? Let me explain it with this question. Can we predict the behavior of DFAs? Or in other words, is the DFA's behavior predictable? What does it mean? Let's say you are an observer and you are looking at a machine. So this is an DFA. And let's say you are in configuration or let's say time frame n. So you are in time n. Can you predict what would be the configuration of this machine at t n plus 1? If you know the configuration of the machine, you have lots of information about that. You know what is on the tape, you know where is the cursor, you know the transition function, the transition graph, and which one is activated, right? So you have all of this information. Now, can you predict that what would be the configuration of the machine at time frame n plus 1? Yeah, that's the important question. So just remember, we are talking about one observer, this guy. Yes, we can predict it with 100% certainty. It means that at any time frame, when you have the configuration of the machine, you can predict what would be the next configuration. So it means that there is no randomness in the behavior of this machine. So why is that? Why is that so? How come we can predict that? Because at any time frame, there is one and only one transition. Yeah, there is no randomness. So if we have this guy let's say this guy is activated and the input, let's say, for example, is A, I know that there is one transition for A, one transition for B, and if it is A, then I know that it goes to this state. So you see, it is 100% predictable. And this is the meaning of deterministic. A machine is called deterministic if at any time frame there is no more than one possible transition. Look at this again. No more than one possible transition. It means that it is either zero transition or one transition at any moment. Why I added zero here? Because we know that for the DFAs, it is always one and only one transition. Yeah, but we have other machines that I will introduce later that in some cases there are no transition in some cases, but still they are deterministic and still we can predict their behavior. So that's why we said there is no more than one possible transition. A class of automata is called deterministic if all of the machines in that class should be deterministic. I'm gonna stop here. See you guys in the next lecture.